Hello guys, this is Dr. Salman Zafar with another video on the Stereochemistry series. Today we are going to talk about chirality and chiral molecules, but our main focus would be how to determine the absolute configuration of molecules. So let's start our today's lecture. First, we need to understand what optical isomers are. So, optical isomers are molecules which have the ability to rotate the plane of a plane polarized light either to the right or to the left. So, molecules which have this property are said to be optically active, and optical activity is a type of configurational isomerism, or optical isomers are configurational isomers of each other. Now, molecules which have this property are said to be chiral, or they are said to have another property which we call chirality. Chirality is derived from a word chir, meaning hand. So it basically means handedness. So if you see your left hand and your right hand, they would look like this. But if you place a mirror right between them, you can see that they look like mirror images of each other, and they are such type of mirror images which are not superimposable upon each other. So if you take your right hand and place it over your left hand, they will not be superimposable finger by finger or thumb by thumb, right? So these left and right hand of yours, they look like mirror images of each other, and this property is known as handedness. Organic molecules, not all of them, but some of them do possess this property of handedness, or in other words, chirality. Now, these molecules which have this property of handedness are known as chiral molecules. Now, this chirality, or this property of handedness, may be because of the presence of a stereogenic center, or a stereogenic axis, or a stereogenic plane. We'll talk about this later on in another video, but for today we will be mostly focusing on how to determine the absolute configuration of the stereogenic center in the molecule. So stereogenic center is a carbon atom or a center within the molecule that has different groups attached to it. So if it is a carbon atom, then it must have 4 different groups attached to it, so as it to be a stereogenic center. And we're going to find out the absolute configuration at stereogenic centers in the molecule. To do that, we have to apply the Kahn-Ingold Prelog system. And as you know already, as I have told you in determination of the E and Z isomerism, that you can find through this link here, Kahn-Ingold Prelog system makes use of the atomic numbers of the atoms directly attached to a particular center in the molecule. So we have to analyze all the 4 groups, or all the 4 atoms that are directly attached to the stereogenic center, and assign them priorities according to Kahn-Ingold Prelog system, or assign them priorities in decreasing order of their atomic number. And that will lead us to determination of the absolute configuration. So we can assign R or S notations to differentiate between 2 stereoisomers or 2 optical isomers of a molecule. R is from rectus, meaning right, and S is from sinister, meaning left. So we will see in a moment how we can assign R or S configuration to these stereogenic centers. Now, molecules are isomers which have one of them have R stereochemistry and the other has an S absolute configuration. They are said to be enantiomers of each other. So isomers that have opposite stereochemistry or opposite absolute configuration at a particular stereogenic center are said to be enantiomers of each other. You might have molecules in which there are more than one stereogenic center. So if the stereochemistry is opposite at all the stereogenic centers present in the molecule, then they can be regarded as enantiomers of each other. But if some of the stereogenic centers in the molecule have similar stereochemistry among the two stereoisomers, then they are not enantiomers of each other. In fact, they would be diastereomers. We will talk about enantiomers and diastereomers in detail later on. And enantiomers are basically non-superimposable mirror images of each other. And as I told you earlier in the property of handedness, that your hands are not non-superimposable mirror images of each other. So in fact, your hands are enantiomers of each other, and the same property is found in molecules as well. So let's see how we can apply Kahn-Ingold-Prelog system to find out the absolute configuration at a particular stereogenic center in the molecules. So the first step is to assign priorities. Now priorities are assigned in decreasing order of atomic number. So we have a carbon atom, a stereogenic center, which has 4 different groups attached to it, and we rank all of them, all the 4 atoms, in decreasing order of atomic number. So the one having highest atomic number will be ranked as priority number 1, and the one having the least atomic number will be assigned as priority number 4. The second step is to orient or draw the molecule in such a way so that the lowest ranked group is away from you. So you know how to draw molecules in 3D on a piece of paper. If you don't know, you can follow the link here and learn how to draw a 3-dimensional molecule on a 2-dimensional screen or paper. So you have to draw the molecule in such a way so that the lowest priority group is away from you. And then you see among the rest of the 3 groups, if you are moving from 1 to 3 in a clockwise direction, the absolute configuration would be R, and if you are moving in anti-clockwise direction from 1 to 3 going through 2, then the absolute configuration would be S. We will explain this with the help of an example here. So you have this molecule 2-bromobutane. Now it's drawn in 2D. You don't know the stereochemistry, the actual stereochemistry of this molecule, like what is the actual orientation of the groups, the bromine, the hydrogen, and the methyl and the ethyl groups in space. So first you need to draw this molecule in 3D. And again, if you don't know, go to this link and learn how to draw a molecule in 3D on a 2-dimensional piece of paper. So now we have drawn this molecule in 3D. So you can see we have a carbon atom right here, and it has a bromine, a hydrogen, a methyl group, and an ethyl group attached to it. So this center has 4 different groups attached to it, and this is a stereocenter right here. Now you can see that 2 of the groups are drawn with solid lines, so that means they are in plane of this screen, and this bromine is drawn with a wedge, and that means it is projected outwards in front of the screen, and this H is drawn with a broken line, with a dotted line. That means it is going into the screen. Again, if you don't know these different drawings or projections, go to the link here and learn how to do it, and then it will be easier for you. So now this drawing or this 3D model of the molecule shows that this hydrogen is moving away from you, or it is projected away from you. Bromine is projected towards you, and this CH3 and the ethyl group, they are right in plane of this screen. Now the first step is to assign priorities. So you see a bromine, a hydrogen, a carbon, and a carbon attached to this stereogenic center. Now looking at the atomic number, bromine has the highest atomic number, so we rank bromine as 1. The second highest atomic number belongs to the carbon atoms, and we have two carbons. So these two carbons cannot decide the priorities. So what we do is that we look at the atom next to this carbon atom. Now this carbon here has 3 hydrogens attached to it, and this carbon has a carbon and 2 hydrogens attached to it. So this carbon here, the second carbon which is attached to this carbon, has a higher atomic number than one of the hydrogens here, and that is why this ethyl group will be ranked as 2, while the CH3 will be ranked as 3, and hydrogen having the least atomic number will be ranked as 4. So you have to draw or orient the molecule in such a way so as to take or orient or project the lowest priority group away from you. And if you look at this model here, the lowest priority group, that is the hydrogen, it already is away from you because it is drawn with a dotted line. So it means it is going into this screen, and that means it is projected away from you. So the molecule is drawn correctly according to the rules. And now you check, moving from 1 to 3, whether you're moving clockwise or anti-clockwise. So you can see it in this way, looking right at the stereogenic center in such a way so that you cannot see the lowest priority group. Right, so hydrogen is right behind this carbon here, and you're standing in a position where you cannot see the hydrogen. And now you see the direction of the direction from 1 to 3, either it is clockwise or anti-clockwise. Now this looks more or less like a fan. If you look at a ceiling fan and you stand right underneath this ceiling fan, you cannot see this hook to which it is this fan is attached to the roof. Now this hook is away from you. You're standing right underneath this ceiling fan, and this hook here is away from you, so we rank it as 4. So this is your priority number 4, and then you assign priorities to the 3 blades of this ceiling fan, and then you check whether you're moving clockwise or anti-clockwise, moving from 1 to 3. So in this case, in this molecule, we have drawn it in such a way so that H is away from us, and now moving from bromine to methyl, we are moving anti-clockwise. So if you are moving anti-clockwise, the absolute configuration is S. So this molecule has S configuration. So you can find the absolute configuration in this way. But if you cannot do it in this way, or you feel it difficult to find the absolute configuration in this way, the other method to do this is to draw the Fisher projection of this molecule. So you already know how to draw Fisher projections for this molecule. I have explained this in another video. Again, you can find the link here. Go and watch that video, how to draw different Fisher projections for this molecule, and that you can do by viewing the molecule from different angles, and that will give you different Fisher projections for the molecule. So if you look at this molecule from this angle right here, then this CH3 and C2H5 will be projected towards you, right? So, and they will look like as if they are on the horizontal plane of a Fisher projection. So if you are standing right here, and in fact you are standing behind this screen facing towards yourself, where you are sitting right now, and you look at this molecule from this angle, this C2H5 will appear as if it is to your right, and this CH3 is to your left, and this H and bromine will be projected away from you if you are standing right here, and H will be appearing as if it is above here, and bromine is right below here. And you already know from a Fisher projection that anything on the horizontal axis means it is projected in front of you, or it is projected towards you or above the plane, and anything on the vertical axis is behind the plane or projecting away from you. And the second rule for determining this absolute configuration through this CIP rules is to orient or draw the molecule in such a way so as the lowest priority group is behind the plane. Now if you look at this Fisher projection, this H is on the vertical axis, and anything on the vertical axis means it is projecting away from you or it is behind the plane. So we have drawn the molecule in such a way that H, or the lowest priority group, is already behind the plane, right? So you can find absolute configuration from here. So if you assign priorities, bromine is 1, ethyl is 2, and methyl is 3. So from 1 to 3, see, you are moving anti-clockwise, so it is S. Again, it means you have drawn the correct Fisher projection. Now if you are standing again in the same position and you are facing towards the screen in the direction in which you are sitting right now, then this CH3 will appear to your right as it is now, and this C2H5 will appear to your left. So they are on the horizontal axis, CH3 to the right, C2H5 to the left, and this time bromine is appearing as if it is up here, and H will appear as if it is down. Now H again is on the vertical axis, so it is behind the plane or projecting away from you. And again, if you imagine it from here, this H and bromine, they are projected away from you. So again, from bromine going through this ethyl group towards methyl group, you are moving anti-clockwise. So the absolute configuration is S. So it means you have drawn the correct Fisher projection. Now you can view the molecule from up here from the two directions. So if you are looking at this molecule from this side, from this angle, now you see this bromine as it is drawn with a wedge, so it is coming out of the screen. This H is going into the screen. So if you are standing right here and looking at this stereogenic center from this angle, bromine will appear as if it is to your right because it is in to the front of the screen, and H will appear as if it is to your left because it is into the screen. So bromine will be drawn to the right, H to the left, and this CH3 will appear as if it is up towards your forehead, and this ethyl group as if towards your chin. So CH3 is drawn up here and C2H5 is drawn down here. Now your lowest priority group H is on the horizontal axis, and that means now it is projected towards you because you were standing here, and you can imagine from here that H and bromine are projected towards you and these two are away from you. And now you have drawn the molecule in a wrong way, in a sense that this lowest priority group H is now towards you, or it is not projected away from you. You can still find the absolute configuration from this Fisher projection even if it is drawn in this way. How to do that? Let's see. So you assign priorities. This is 1, this is 2, and this is 3. Now moving from 1 to 3, you are moving clockwise. But because you have drawn the molecule in the wrong way, means that H is projected towards you. It should have been away from you, but you have drawn it in such a way that H is towards you. Now in this case, moving clockwise from 1 to 3 would mean S configuration. Otherwise, if H would have been away from you or behind the plane, then this clockwise movement would mean an R configuration. But in this case, because you have defied this rule, so you have to defy the second as well to get to the correct absolute configuration. So in this case, you are moving clockwise, but because H is above the plane, it means this clockwise rotation means S configuration. Now if you stand right here and look at the molecule, from this angle, this H will appear as if it is to your right and bromine to your left. So again, they are on the horizontal axis, H to the right, Br to the left. This time C2H5 is up, CH3 is down. And again, H is on the horizontal axis, so it is above the plane. And we have to follow the same rules as we did for this Fisher projection. So from 1 to 3, you're moving clockwise. Now because H is above the plane, clockwise in this case would mean S configuration. So your Fisher projections are right. From any of these Fisher projections, the absolute configuration is S. That means you have drawn all of them in the correct way. Now for these two, in which the H is, or the lowest priority group, is on the vertical axis, it is easier to find the absolute configuration. But if you cannot find absolute configuration correctly from these two Fisher projections in which H is on the horizontal axis, you can actually take this H on the vertical axis, and there are certain tricks to do that. You can find the absolute configuration from here as well, but if you find it difficult, you can draw another Fisher projection in which this H is on the vertical axis, and there's a method or two to do that. So let's see how we can take this lowest priority group behind the plane, or take it onto the vertical axis if it is on the horizontal axis in this case, right? So you assign priorities and you see that your lowest priority group H is on the horizontal axis. You have to take it onto the vertical axis, either up here in place of CH3 or in place of C2H5. So you can do this in 2 steps, or you can do this after 2 exchanges. So the first step is to exchange this H with BR. So you exchange H with BR, H comes here and BR goes there, and so this is the new Fisher projection. But this is not the end. You have first exchanged BR with H, CH3 and C2H5 are still in their same place, and H is still on the horizontal axis. You have to take it there. So in the second step, what you do is you exchange this H with CH3, and so it looks like this. And now your lowest priority group is on the vertical axis, or it is behind the plane. And now after assigning priorities, you can see that from 1 to 3 we are moving anti-clockwise. So the absolute configuration is S, as was for the molecule drawn in 3D. And so this exchange has worked well, and we have taken our lowest priority group behind the plane, right? For the second Fisher projection, in which H was to the right and BR was to the left, again we want to take this H up here. So first you do an exchange with the BR, again as we did in this case. So you exchange H with BR, so H goes to the left, BR comes to the right, and then you exchange H with C2H5, and as a result we have this Fisher projection. So now H is on the vertical axis, it is projected away from you. And now you see after assigning priorities, moving from 1 to 3, again you are moving anti-clockwise. So the absolute configuration is S. So this is a trick how to take your lowest priority group behind the plane, or take it onto the vertical axis in a Fisher projection. There's another way to do it, and that is after assigning priorities. If you see that your lowest priority group is on the horizontal axis, what you do is you exchange it with the CH3 here, right? But at the same time you have to exchange the other groups, the 2 groups as well. So you exchange H with CH3, so CH3 comes here, H goes there, and Br comes here, C2H5 goes there. So this is how it looks like. And now you have done it again in 2 steps. You have taken this lowest priority group onto the vertical axis, and now again moving from 1 to 3, you're moving anti-clockwise. So the absolute configuration is S. For the second Fisher projection, again you can exchange H with C2H5 here, and then you exchange Br with CH3. or you can exchange with the CH3 as well. So you take it to the upper portion in the on the vertical axis, or you take it down here. It doesn't make any difference. So you exchange Br with this, H with CH3, and this is how it looks. So now H again is on the vertical axis, meaning it is behind the plane or away from you. And again, from 1 to 3 we are moving anti-clockwise. So the absolute configuration again is S. So first you have to draw the molecule in 3D and then orient or project it in such a way so that the lowest priority group is behind the plane. You can do it from the 3D projection or from the Fisher projection. In cases where the lowest priority group is towards you, projected towards you, clockwise rotation would mean S and anti-clockwise would mean R. But in cases or projections in which the lowest priority group is behind the plane or away from you, clockwise would mean R and anti-clockwise would mean S. You can determine the absolute configuration in both cases, but if you still want to take your lowest priority group behind the plane or bring it onto the vertical axis in Fisher projection, you can follow these two steps and you can bring it onto the vertical axis. Now you have this molecule drawn in 3D, right? If you place a mirror in front of it, its mirror image would look like this. So you see Br drawn with the wedge here, again with the wedge here. It is projected towards left, so this would be projected towards right in the mirror image. Similarly H and CH3, C2H5. So these two appear as if they are mirror images of each other. H here is projected away, so 1, 2, 3. We're moving anti-clockwise. This is S, it's the same molecule. But if you analyze this molecule, H again is projected away from you, and now from 1 to 3 you're moving clockwise, and this means the absolute configuration here is R. And as I told you earlier, if two molecules have opposite stereochemistry or opposite absolute configuration at all the stereogenic centers, in this case there is only one stereogenic centers, then they are enantiomers of each other. So these two molecules are enantiomers of each other, and this enantiomer of this molecule is actually its mirror image. And what sort of mirror image? It is a non-superimposable mirror image of this molecule. So you see, if you want to superimpose it, see the H is not superimposable upon H, Br is not superimposable upon Br, and so are the other groups. So these two are not superimposable mirror images of each other, and that is why we say they are enantiomers of each other. Molecules which have more than one stereogenic centers will have more number of stereocenters or more number of stereoisomers possible, and this is the formula from which you can determine the total number of stereoisomers possible for a molecule. So if you have only one stereogenic center, as in this case, 2 raised to the power 1 means it can have two possible stereoisomers, as we saw here. If you have two stereogenic centers, then a total of 4 stereoisomers are possible. Among all of these stereoisomers, only 2 would be enantiomers of each other. All the rest would be diastereomers of the others. So this is how you can determine absolute configuration or assign R or S configuration to a stereogenic center in a molecule. We will talk about the stereogenic axis later in another video. Thank you for joining. Stay tuned for more videos in stereochemistry.